So we have introduced the concept of thermodynamic potentials as a set of 4 or 5 new functions, state functions, which will be helpful in studying the equilibrium properties of a system. As I told you, the concept of thermodynamic potentials, a set of potential functions, was borrowed from the concept of potential or potential energy in mechanics. And you know what is the relevance of potential in mechanics? We have seen that in mechanics, for a system to be in equilibrium, there we call the equilibrium to be mechanical equilibrium. The condition is that the potential energy V will be attaining its minimum value. Potential or potential energy will be attaining its minimum value. So V equal to V minimum under the condition of mechanical equilibrium. So the minimum value of potential energy helps us to identify the state of mechanical equilibrium. Similar to that, the minimum value of some quantities or some functions in thermodynamics will help us to identify whether or not a given thermodynamic system has attained equilibrium. You know, there are several types of equilibrium in thermodynamics. So depending on the constraints or depending on the situation, one out of the 4 or 5 functions or potentials that we have discussed will help us to identify the equilibrium properties of a system. And the first one that we are going to discuss is internal energy function, represented by U. And we will be doing in this way. We will first define the function, and since internal energy is already defined, we will just restate that definition, and then we will discuss some of the main properties of the thermodynamic potential introduced in this session, and we will discuss the further properties or more discussion on the same thermodynamic potential will be done in a separate session. Okay, so to begin with, the concept of internal energy was introduced in your second module, where we discussed about the first law of thermodynamics, and we introduced internal energy function as a state function. Okay, so it's a state function, internal energy function. U is a function of the coordinates of the thermodynamic system, whose value at the final state minus the value at the initial state is equal to the adiabatic work done in going from one state to the other. And that is how we defined the internal energy function. Hope you remember that. UF is not, this is the way in which this is the mathematical state. UF minus UI is equal to W adiabatic. Hope you still remember this equation. We have discussed this equation in the beginning of our course. So delta U or du, okay, in the case of infinitesimal changes we will call it as du. In the case of finite changes we will call it as delta U. See, suppose that the thermodynamic system has got 2 states. That is, okay, it has got one initial state, okay, and a final state somewhere. It can be described in the PVT diagram also. So some coordinates, you can just take some favorable coordinates. So system is having an initial state, system is having a final state. And see, there is a function defined for the system represented by U, which has got certain definite value at initial state and certain other value at the final state. And if the if the system is made to change its state by performing adiabatic work only, okay, so under adiabatic conditions the system is made to change from initial state to the final state, suppose that. So the work that is done during this adiabatic process can be directly calculated by subtracting the initial value of this function ui from the final value of that function uf. So if there is such a function, that mathematical function was identified or named as internal energy function. Okay, and hope you remember actually how do we arrive at this particular thing. That was just from a modification of the first law of thermodynamics, and the first law of thermodynamics was stated like, see, du is equal to, right, okay, du is equal to d bar q plus d bar w, and hope you remember that is a general okay, mathematical statement of the first law of thermodynamics. And you know that for adiabatic processes, this d bar q will be equal to 0. Okay, so it will be simply du is equal to d bar w, right? Du equal to d bar w. So here in this equation, d bar w is the adiabatic work done. Okay, and that is what we have done. Okay, for finite changes, we have written du as delta u, and delta u is equal to, so this is for a finite process, this will be just written as what? Adiabatic. So delta u equal to w adiabatic. So this is the way in which we define the internal energy. So recall the internal energy function definition. This was the same thing that we had done earlier. It is a function of the coordinates of the thermodynamic system, like the pressure, temperature, etc., whose value at the final state minus the value at the initial state is equal to the adiabatic work done in going from the initial state to the final state. Or this equation is the defining equation of internal energy function, which is now identified as one of the potential functions, one of the thermodynamic potentials. Okay, now one thing to keep in mind, this internal energy function, it represents the, in a way we can say it represents the heat content of the system at constant volume. It represents the heat content of the system at constant volume. We will be justifying this particular statement. Okay, you can justify this statement in one particular way. Say, for example, you have got this equation. Is not? I'm just using this equation du. So this is the first law of thermodynamics. So du equal to d bar q plus dw. So can't you rewrite this equation? Just let me make some space. Yeah. See, we can rewrite this equation. How do you rewrite this equation? So this equation can be written as d bar q, right? D bar q, and d bar w can be written as minus p dv, right? Minus p dv, as per the convention that we are using, d bar w equal to minus p dv. Now do one thing. Let me divide du with dt. So I'm dividing by dt on all sides. So what do you think? It's equal to d bar q over dt. Okay, minus p dv by dt. dv by dt. Now if you keep volume as a constant, see, if volume is kept as a constant during any process, if volume is a constant, then this dv in the equation will be equal to 0. So this term will be vanishing. So what are we getting? Therefore I can write, okay, since I am keeping one of the variable as constant, let me represent this total derivative as a partial derivative. Dou u with respect to dou t, dou u with respect to dou t, under what condition? Constant volume condition, v equal to constant. It will be equal to dou q or dou bar q, whatever it is, by dou t under constant volume, under constant volume. And what is this quantity on the right side? Dou q by dou t at constant volume, and this is nothing but, we had defined this one as nothing but Cv. Okay? So, and don't you know that Cv, the heat capacity of a system, not a measure of the heat content of the system, and that too under what condition? That too under constant volume condition. So you can see that this Cv, which represents the heat content of the system under constant volume condition, actually related to this variable. Which is that variable? That is the internal energy. So that is one reason why we say that internal energy function represents in a way the heat content of the system at constant volume conditions. Okay, so we'll see that when we discuss the enthalpy, which is yet another thermodynamic potential, we will see that enthalpy will represent the heat content of the system. It also will represent the heat content of the system, but not under constant volume condition. Instead, it will be the heat content of the system under constant pressure conditions. Okay, And usually the internal energy function is so familiar to us that we do not use this heat content at all, because we are much familiar with the concept of internal energy in some other way also. So we define internal energy as a sum total of the kinetic and potential energies of all the constituent atoms and all that. So we have some other way defining internal energy of a system. That's why we do not usually use the idea of heat content whenever we discuss about internal energy function. But remember, mathematically, internal energy is related to the heat content of the system under constant volume or isochoric conditions. Okay, we will make this idea more clear when we discuss the enthalpy in the next slide. Okay, so now let me come back to the internal energy function. See, whenever we discuss a thermodynamic potential, we will be defining what is known as the natural variables. We will be defining what is known as natural variables of the function. Let me see, or let me tell you what actually is meant by natural variables and how it will be useful. Okay, see, let me use this one. So equation 1 is the defining equation of internal energy. So let me use the first law of thermodynamics again. So from first law of thermodynamics, first law of thermodynamics, what equation do you have? You have du is equal to d bar q, I can directly write d bar q minus p dv. Okay, d bar q minus p dv, this form of the equation, right? Now see, I'm going to bring in the quantity of entropy here. In this equation, I can rewrite this equation in terms of the entropy. Okay, how do I bring in the entropy? So for a reversible process, you know, the entropy change involved is related to the heat d bar q upon T. So this is the the entropy change involved during a reversible process involving a heat transfer d bar q. So we consider all these cases as reversible cases, you know. It's an idealization that we are discussing. Since ds is equal to d bar q by t, wherever you find d bar q in all these expressions, you can rewrite this one as tds. Okay, so I'm rewriting this equation as tds and minus the same thing, minus p dv. So this is my third equation. That's my third equation. So just remember, so this is an equation that is worth remembering. So du is equal to tds minus pdv. And remember, this is nothing but the first law of thermodynamics, terms of the entropy change of the system. So from this equation, I can make a mathematical conclusion. I can say that the function u in the equation number 3 can be expressed as a function of two variables. Which are the two variables? One is s and the other is which one? V. So I can write, or I can express the internal energy of the system as a function of two specific variables, two very definite variables, which are s and v. Okay, S is the entropy and V is the volume. So this is yet another fact or another relation that I want you to remember. We will be summarizing all these things in the final slide, which will give you a clear picture. Now we are developing the thing from scratch, from here and there. Finally, I will put it together so that we will get a holistic picture of what we are actually discussing. Okay, now you may feel that there are a number of scattered equations which doesn't give you much meaning, but okay, I can assure you that finally I will give a particular meaning, because these are something demanding. That's something. Okay, so u is equal to u of sv. And remember, this s and v, which are already defined, s and v, which are already defined thermodynamic parameters, are known as, so this s and v are known as the natural variables. They are named as the natural variables of u. S and v are, so don't please just mistake this one by u. Okay, so s and v here are known as the natural variables of u. It means that you can actually express U in terms of some other variables. You can express U in terms of pressure and volume, okay, temperature and volume. So you can write all U in terms of many other variables. Okay, which are the other variables that we are already discussing? We are discussing about pressure, volume, temperature, entropy, etc. So these are the functions which are already state functions, which already we have got definite meaning. And what we are doing, we are defining now new variables, new functions in terms of any pair of variables here. Either I can combine P and V, I can define a new function of V and T, I can define a function of T and S, I can define a function of V and S. So there are several choices. So which function we have defined? We have chosen, we have defined a function of V and a function of S. And that function U is equal to U of SV is regarded as one of the thermodynamic potentials. I think it's time that you revisit our definition of thermodynamic potential that we have used in the previous session. Okay, so remember U, one of the thermodynamic potential, the first thermodynamic potential we have written as a function of S and V. So now let's go back to our previous slide. See, what is the definition of thermodynamic potential we have used? Thermodynamic potentials are certain functions, for example U, of thermodynamic coordinates P, V, T and S. We won't use all of this, we will be taking only two of them. That is enough. You need not use all the variables. So here we have taken out of this one V and S. Okay, so U is a function of V and S, which together with this equation and this equation. Can you see that I have used dq is equal to du plus pdv, or du equal to dq minus pdv, which is nothing but the first law of thermodynamics, and also I have substituted as dq equal to tds. Enable a complete knowledge of the state of the system, and this one we have to justify. This second part of the definition I have to justify. So this is what we are defining. So one of them is U. U is a function of V and S. Okay, and we will. So this is one. This one only we are discussing now, and we will see that H is a function of P and S. Okay, so we will define that H is a function of P and S. Okay, A is a function of this is what we are going to see. A is a function of V and T, and G will be a function of P and T. So you can see that several combinations are coming up. Okay, all these are what is known as the thermodynamic potential. So this is what we have done. Okay, let me do the original discussion that we have done. So U is a function of S and V, and S and V here are known as the natural variables of the internal energy when it is expressed as a thermodynamic potential. So let me just give you a word of or a important thing. Say caution. Why I say caution? Because you should be careful about this one. I told you that U can be expressed in terms of other variables as well. That's what we have been doing. In the case of ideal gas system and all, we have been writing U in terms of the volume, temperature, pressure, etc. So for example, I can write U as a function of volume and temperature. Okay. Now, we will be getting other information, or we will be getting information about other quantities from this one. But what you will have to do, you will have to perform some certain kind of integration and all. And once you write U as a function of V and T, then U will not be given the status of a thermodynamic potential. See, I repeat, U will be regarded, or U will be given the status, special status of a thermodynamic potential with all its benefits and properties, if and only if that U is expressed as a function of entropy and volume of the system. And if you are expressing U as a function of volume and temperature, then that is not going to get the status of thermodynamic potential. That is something important. And that is why S and V are called the natural variables of U. Natural variables. That is a pure variable. Okay. If you are able to write the internal energy, if you are able to express the internal energy of a system in terms of its entropy and its volume, then that function is a complete function, and that function is full of meanings, hidden meanings, and that much information will not be available from the quantity or from a function if it is expressed in terms of some other variables like volume, temperature, pressure, volume, pressure, temperature, etc. You can do, because all these are mathematical functions. Okay, so that's something. So u, if expressed as a function of other variables other than the natural variables of u, then we will not regard that u as a thermodynamic potential. And that is one reason why, even though we had introduced internal energy earlier in our discussion, we again introduced internal energy along with other newly defined functions like Helmholtz free energy and Gibbs free energy. That is one reason why we are doing it, because now we elevate internal energy to another status. The status of internal energy function has been elevated because it has been given supreme importance. It has been included amongst one of the very powerful functions in thermodynamics, or one of the potential functions. I can use the word potential function. Potential means having capacity, is it not? So when you express u as a function of s and v, this function has got capacity to give more information regarding the nature of the system, especially the equilibrium properties of the system. Now let me just write some derivatives of equation number 3. So that so that is one word that you have to remember. This quotient you remember. Now from equation number 3 I can just get some derivatives. How do I get derivatives? I can write from this one, t is a thermodynamic variable and p is a thermodynamic variable, you know. Okay, so using this equation 3, I can write that temperature of the system T will be equal to dou u with respect to dou s. Temperature of the system will be equal to dou u with respect to dou s. Under what condition? Under what condition? Under volume is equal to constant. See, v equal to a constant. See, don't confuse between u and v in my handwriting. T is equal to dou u by dou s at v. And another relation. How do you define P from this relation? P will be equal to dou u. I think you are following me what I am writing, how I am writing. Dou u with respect to dou v. Dou u with respect to dou v. Try to identify what I am doing at constant s. So these equations let me call by some equation number 5, these two equations. So these are the derivatives of u. These are the derivatives of u. And can you see that now u is such a function from which I can obtain the values of temperature and the pressure if you are expressing u in terms of its natural variables s and v. How do we get this equation number 5? This is what I have done. So you can look at du. Look at equation number 3. See what I'm doing initially, I'm keeping volume constant. Right? When you keep volume constant, what will be dv? dv, when v equal to constant, dv will be equal to 0. So this term will be 0. When this term is 0, what is remaining? You get du equal to tds. So from that, can you write what is t equal to? T will be equal to du by ds. But you know, it's not a complete differential now because we have made the second term equal to 0 by setting v equal to constant. So instead of writing as a complete differential, I will write as a partial differential and putting v equal to constant here, right? The reverse we have done to obtain this second equation. You wanted to define pressure, and pressure is the coefficient of dv here. So what you have to do? You have to get rid of the other term. So to get rid of the other term, you make ds equal to 0. How can you make ds equal to 0? You put a constraint, you put a limitation or condition that entropy is equal to constant, and that's what I have done here in this expression, s equal to a constant, right? So when s equal to a constant for the process, or when the process is isentropic, this tds term will be equal to 0. So you are left with a du equal to minus pdv. There is a minus sign here, don't forget. Du equal to minus pdv. So p will be equal to, you take the minus to the other side, it will be equal to minus du by dv, but under s equal to constant. So I will write to say partial derivative. So P equal to S, please. That is one thing. There should be a minus sign here that I had missed out. P equal to minus dou U by dou V at a constant S. So you can see that this knowing the internal energy in terms of the entropy and volume will let you find out or define the temperature and the pressure of the system in terms of the internal energy. So we can say that internal energy helps us to obtain other things. So this is the definition of internal energy function as a potential function. We will see more of its implications in the coming discussions. So my aim is first to introduce this concept one by one, and thereafter we'll go to the other other detailed discussions. And before just I wind up this particular session, let me tell you one idea that the other three thermodynamic potentials, namely, which are the other three remaining? So I'm intentionally repeating them so that it strikes your memory. I'm intentionally repeating the thermodynamic potential. What are the other three? The other three are the enthalpy H, the Helmholtz free energy A or F, and the Gibbs free energy G. These three are obtained from the already defined internal energy function, or H, A and G are derived from the already defined U by certain mathematical techniques, and that is permitted. And that technique by which you can define new mathematical functions which are equivalent. Equivalent means what? Whatever information that is hidden in U will be hidden in H also. That will be available in A also. That will be available in G also. Means you will be having information regarding the system hidden in all these functions. But one function will be suitable for one context or one situation, and the other function will be a better one or convenient one for dealing with another situation or another set of constraints. So there are mathematical techniques to obtain equivalent functions. Remember, I'm not using equal functions. So there is a mathematical technique to obtain equivalent mathematical functions from one existing function by a certain technique, what is known as Legendre transformation. Legendre transformation. Legendre transformation. Whenever I use the word Legendre transformation, remember, it's a mathematical technique of finding out new but equivalent functions from, so that it will be useful for some other, and that is done by the mathematical technique known as transformation. I will introduce the in a later video so that you get it. That is something very, very important, even though you need not background, but you should always remember, or you should understand defining other things. Should I by heart all strong mathematical? So I will do that one. And Legendre transformation is a mathematical technique to define new but equivalent function if we are in need of that. Equivalent function, because see, the new point to define in the next H will be equivalent to U. Equivalent to A, to G. So all these functions with thermodynamic potentials are equal. All of these functions can regarding the equal. So for the same system we can define H. It will have some other value for A. It will have some. Will be able to get information regarding the system. From U you can get get it. But the information will be different when you define thermodynamic potential. Okay. That's about the function in the next video.